In Chapter 9, we're going to start talking about estimating a population proportion. Okay? So at first we have to decide what makes a good estimator of a population characteristic. And our population characteristics so far have been proportions, right? So we need to know that we have a good estimator and that it is an unbiased estimator of a of that population characteristic, and understand how the standard deviation of that sample proportion is related to sample size and to the value of that population proportion. Then we're going to find our margin of error and look at that relationship between sample size and that also, and maybe look at how we use an interval to estimate a population characteristic. So a little bit of this we did in Chapter 8, and we're really going to talk about how it works in Chapter 9 and actually create a confidence level, a confidence interval, and a confidence level associated with that confidence interval. So the first thing that we need to ask ourselves is, what makes a statistic a good estimator? Okay. And we're going to talk about what it means to be an unbiased estimator. So a statistic with a sampling distribution that is centered at the actual value of the population characteristic is what we call an unbiased estimator. Right, so if we had the sampling distribution was centered at the actual value of that population characteristic. So basically, in other words, the statistic doesn't consistently tend to underestimate or overestimate the value of that population characteristic. That is an unbiased estimator. Okay, so which of these looks like an unbiased estimator to you? Is the distribution here, is the mean of the distribution at the true value of the population characteristic? No. Here it is, and here it is. So these two would both be unbiased estimators. The first one would not. Okay, so once we have an unbiased estimator, the distributions could look, something similar to this one in the center and the one in the right. And which one would be better? Well, if we think of the spread now, the standard deviation of the sampling distribution is what we call the standard error. So the standard error is just a standard deviation. Well, we know that the bigger the standard error, the bigger the standard deviation, the more variability there is. So if we can get a tighter clustering around the true value, then we would have less of a standard error, right? So we can think, if we look at this, we notice that the middle distribution has a larger standard error than the one on the right. If a sampling distribution is centered very close to the actual value of the population characteristic, we say a small standard error ensures that the values of the statistics will cluster tightly around the actual value of the population characteristic. A statistic that is unbiased and has a small standard error is likely to result in an estimate that's close to the actual value of that population characteristic. Okay, so let's take a look at an example to kind of get an idea of how these numbers work. So, in a review of all criminal cases heard by the Supreme Court of 11 states from 2000 to 2004, it was found that 391 of the 1,488 cases were decided in favor of the defendant. So this is all of the criminal cases. So this is not a sample. This is the actual population. So we will find P, the proportion of all cases reviewed that were decided in favor of the defendant, and that's just this fraction, 391 over 1,488, which is 0.263. So suppose that the proportion was not known, right? Because if we know the actual proportion, there's no sense in doing any statistics, taking a sample. But what we do is to kind of learn about how these numbers all work together, we take things that we actually do know and we look at what happens when we take different kinds of samples to kind of learn of what's going on. So suppose that you selected a sample, computed P hat, which was the sample proportion that were decided, in terms of the defendant. So let's first say that n equals 25. Okay, so the standard error, remember, is just the standard deviation of the sampling distribution. The standard deviation of that sampling distribution is P times 1 minus P divided by n. Okay, so if we really were able to calculate this, right, since we actually do know what P is, we would put 0.263 in and 1 minus 0.263 divided by 25. Then take the square root of that. And if we calculate that, we should get a standard error of 0.088, 8.8%. Okay. Now, what would happen if instead of taking a sample size of 25, we increased the sample size to 100? Well, the standard error is still the standard deviation of the sampling distribution, which is still going to be P times 1 minus P over n. And we take the square root of that. But this time, the only thing that's going to change is that denominator. So in a fraction, when you make the denominator bigger, it actually makes the whole number smaller, right? So when we calculate this, we should get 0.044. So we get, the standard error is 4.4%, as opposed to the 8.8% when we had a sample size of 25. So what does that tell us? It tells us that, therefore, the larger, the three little dots that make a triangle means therefore. So I tend to do that sometimes just so I don't have to write it out. The larger sample size, the smaller the standard error. So sometimes when statisticians are designing experiments, they need that standard error to be pretty small. And so they will figure out what sample size they would need to ensure that they have a very small standard error. Okay, so now let's pretend that instead of P being 263, P is 0.04. Okay. When n was 25 and p was 0.263, we found the standard error to be 0.088, right? So what we want to do now is see how does changing the p affect the standard error. So let's check this out. Find the standard error, but now we're going to assume that this is 0.4. So we have 0.4 times 1 minus 0.4 all over 25. That is equal to 0.098. So the standard error has increased. So what actually is happening here is that the standard error changes and gets bigger as p gets closer to 0.5. As p gets closer to 0.5, the standard error increases. Okay. In comparing these, we didn't change n, right? We only changed p. Now let's pick a p-value that is really small and it's far away from 0.5. And let's calculate the standard error now. So this would be 0.04 times 1 minus 0.04, which is 0.96, all over 25. When we calculate that, we get a standard error of 0.039. It's very small. So what happens here? As p gets far from 0.5, the standard error decreases. Now, and that really comes from the formula, right? This is what's happening. You have p times 1 minus p in the numerator over n. If we're just changing the p's, the biggest that number could be is when p is 0.5, because we would have 0.5 times 0.5 over n, right? If p is 0.6, like we had p is 0.4 over here, we would have 0.6 times 0.4 over 25. That's still going to be smaller than 0.5 times 0.5. So the biggest that the standard error can ever be is when the population proportion is 0.5. Okay? And that's what we say for a fixed sample size. The standard error p hat is greatest when p is equal to 0.5. And that's just because mathematically that's the number that's going to make that standard error the largest. Okay. So